To first thank the organizer for giving me the opportunity to present my work, for which I also want to thank my co-workers from the Professor Day group at Southampton University and Professor Emsley group at EPFL. So I'm going to talk about machine learning for molecular materials. And so first, molecular materials are basically molecules on a lattice arranged with a certain arrangement, and this the stability of this arrangement is driven by the competition between different non-covalent interactions, such as van der Waals pi-pi, something which looks like this, pi-pi interaction, hydrogen bonding, as you can see here. And all of these interactions are quite relatively weak, and for the result of this relative weakness is that many of these molecular arrangements are actually stable. We can at least observe them, which so many of these polymorphs that can be observed have very different properties. It's just as an example, the dissolution rates of a drug is highly influenced by which polymorph has been crystallized, or the charge mobility of an organic semiconductor is also heavily influenced by which polymorph is actually there. So the study of the curve of the polymorphism is molecular solids is quite important. So to study this polymorphism, one way is to go through the crystal structure prediction. So you theoretically generate sample. So this is one of the examples of how one would do it in the crystal structure predictions. So you generate a lot of possible crystal piping by sampling the crystal packing variables, and you relax all of these structures. So as you can imagine, there are many possibilities. So this involves many calculations that need high level of accuracy, since what we are looking for are lattice energies. So then we want to have all of these non-covalent interaction right, or at least as well as possible. And the second challenge, I would say, is you end up with many calculations. How do you rationalize this big amount of data? So these are the two things I will be talking about. And in the second part of my talk, I will try to show you how you can also help with machine learning actual interpretation of experiments. So if you want to investigate what is the polymorph that has been synthesized, one of the state-of-the-art techniques is solid-state NMR spectroscopy for powdered molecular crystals. And what you end up with is a spectra of the chemical shift. So let's say here is the chemical shift of proton. So you apply a very large magnetic field and some perturbation, and the chemical shift is basically the magnetic response of this atom to the external magnetic field, and this response is heavily influenced by its chemical neighborhood. So the protons in this case become a probe for the local structure. And but unfortunately, in molecular crystals, the arrangements are very complex, and there are many possibilities. So the typical framework of an experimentalist is actually to run many GPO-DFT calculations to predict the chemical shift of many possible polymorphs, and they compare the predictions with the experiment, and the one that matches the most of the experimental values is is the structure that they are observing. Okay, so the tools that I will be using is the SOAP and the REMatch kernels for the representation. So for the SOAP kernels, briefly, so you represent an atomic neighborhood by sampling on an atom and putting Gaussians in the surrounding, and then you compute the similarity between these two local environments by computing the overlap integrated over all possible relative rotations of these two local environments. So this is the measure of environmental similarity, which is very good for the chemical shift, since it's a property associated to the center. But if to predict stability, you want to combine all of this local information into a global measure of similarity, for which I use the regularized entropy match kernel. So it's basically a way of finding this weight, so that you want to weight a bit more the best matching environment and weight a bit less the environment that are not so well matching. And there is an internal parameter to switch from how much you want to weight more the best matching environment. Okay, and then for the predictions of the property, I will be using kernel grid regression so with either the SOAP kernel or the SOAP and REMatch kernels, and to analyze to understand, to try to rationalize the databases, I will be using a clustering technique called HDB scan. So it's a density-based clustering technique that uses single linkage agglomerative hierarchical clustering. And to represent in an intuitive way the databases, I will be using the sketch map dimensionality reduction technique, where you project from a large feature space where your molecule or your structure live onto a 2D map that you can easily explore afterwards. Okay, so the data sets I've been working on were provided by Jack Young and Jeremy Dale. So these are a Pentacene molecular crystal and two substituted Pentacene called other Pentacenes. And the Pentacene system is of a very is quite interesting because for its application on organic semiconductors, and because we expect that if it is crystallized in this kind of face-to-face arrangement, the charge mobility would be quite high. Unfortunately, it turns out that this is more of a face-to-side packing that is favored. So that's which motivates this particular type of chemical substitution. So here are the energy, the stability predictions. So these are the learning curve done on the full data set. So all the parameters were estimated with five-fold cross-validation, and the generalization error was obtained by averaging over many models. So as you can see, we reach quite a good level of accuracy with about 1 kilojoule per mole. But then you ask the question, the three systems seems very similar when you at least look at the molecule. So why the discrepancy between this learning curve? Why is the 5B system much harder to learn as it seems? So one way is to use a sketch map. So let's this is a tool that we have developed for interactive exploration of the sketch map. So let's say you have all of the sketch map and you browse a little bit around and you see, oh, that there are these molecular clusters. It doesn't update. Oh, sorry, but okay, and so then you will identify the fact that you have these two clusters that seems to pop out. So this is a low energy cluster, so it corresponds to the phase that I was talking about, the herringbone phase, and there is the other cluster. But this is very cumbersome because you have to look at this cluster, and in this particular case, the sketch map is not so clear. You don't really. It's hard to understand what is a cluster and what is just a deviation of from the. So to automate this procedure, I'm using the AGB scan clustering technique. So you cluster in the high dimensional space, and then I color the cluster found on the sketch map, and you automatically find all of these phases. So note that the structures that are not colored are not associated to any cluster because they are in the high dimensional space. They are in they don't have many neighbors, or they might be even quite far away from others. So they are not let's say a recurring motif within this database. So now, how do you assess? Can you use this tool to understand the effect of the chemical change on the Pentacene systems? As you can see here, the data sets, the clusters that are found are all of the layer type, so face-to-face kind of arrangement, and this corresponds to 70% of the data set. So most of the data set is clustered, so it's quite an homogeneous system, and you observe that this particular chemical change actually did favor the face-to-face kind of packing. On the other hand, for the asymmetric type of chemical change, you can see only 10% of the data set is actually corresponds to a recurring motif. So most of the data set is an outlier, let's say. So most of these structures are quite different from each other, at least using our soft representation. And yeah. So that's now I'm moving on to the prediction of chemical shift. So that there were no existing databases of chemical shift for molecular solids. So we took all the entries from the Cambridge structural database that have less than 200 atoms per cell, because the GPO calculations are quite expensive, and we are selecting hydrogen, carbon, oxygen, and nitrogen, about 60,000 molecular crystals, and we select from these 2,000 molecular crystals that we deem as most diverse using the similarity measure of the soap kernel, and we randomly select a test set of 500 entries. Okay, so here is I'm showing you the learning curve. So all the parameters have been optimized on the training set with a threefold cross-validation. So there are 2,000 structures, but let's say for hydrogen here, I'm showing the RMSC for the prediction on hydrogen. It's about 70,000 hydrogen, so properties. So that's why here threefold cross-validation is already quite good. And I'm showing you the learning curve for different cutoff radii. So as you can see, the kernel with a 2 angstrom radius cutoff almost does not, it predicts something and doesn't learn anything afterward when you increase the number of structures. While the kernel with a 3 angstrom cutoff learns, but tends to saturate with a large number of training structures. While on the opposite, the kernel with 7 angstrom cutoff is not performing very well compared to the other, but it keeps learning until the 2000 structures. So we took the idea from a previous work on combining, making a linear combination of these kernels. We call this multi-scale kernel with these particular weights. And what's surprising is that the best weights were, the kernel that weights the most is the 2 Armstrong kernel that was not learning anything, but it's actually the ones that weights the more to get an improvement of about 20%. So here I'm showing you the comparison, so the training on the whole training set and testing on the 500 testing structures. And this is the difference in chemical shift between our predictions and the GPO predictions. We reach about a RMSE of 0.49, and actually some previous work estimate the accuracy of the GPO calculation of about 0.5 ppm too, so we are within this ballpark. On the other hand, for carbon, we are still a little bit off, but we are working on it to get better predictions. Now I'm showing you the comparison with experimental results. So here is our chemical shift prediction with respect to the experimental chemical shift for these all of these chemical compounds that are molecular crystals, of course. And as you can see, we are again, most of our predictions are within the accuracy of. So maybe, yeah. So just to show you the timings of our calculations, and as you can see, if we project with a cubic interpolation, we project to actually predict for cells of 1,000 atoms. It would take about 1.5 years. So of CPU time. Our ShiftML predictions can actually, with quite a good accuracy, predict these chemical shifts. So explore larger cells, larger molecular crystals arrangements. And now this is, I would say, the main result. So it's a bit complicated. So that's the typical way of finding which is the candidate structure that is actually matching with the experimental the experimentally observed polymorph. So here is the LMSD from the GPO predictions and the ShiftML predictions with respect to the experimental results for each of the candidate structures. And as you can see, we are doing here is this gray line is the uncertainty of the inherent uncertainty of the method. And so if you are predicting something around here, then it means that this is likely to be the structures. And we are doing as well as GPO-DFT for doing structure prediction in both the case of cocaine and SLD, which is pharmaceutical compound. So with this, I would like to thank you. And if you are interested in the interactive sketch map, you can browse this website and the GitHub repository to build your own sketch maps, interactive sketch maps. And you can also check out shiftml.epfl.ch to upload your molecular structure and find some predictions. Thank you for your attention.
So, any questions from the speakers? Yes?
On the previous slide, you had this RMSD. What's that? Is it root mean square deviation?
Yes.
Okay. So how is it different from root mean square error? Or
it's the same. Yes. It's yeah.
Yes.
So this learning curve, which says if you've got a 2-angstrom cutoff, you get 1.5 ppm or so. Do you understand correctly that it's the cutoff on your hydrogen or something? So you're basically just seeing the nearest neighbor.
Yes.
And and the follow-up question is, when you want to compare this to experiments, how bad does that kind of error hurt you? Like, how precise would you want your model to be able to predict it? Because I don't do experiments, so I can't tell you how bad is 1 ppm error.
So they estimated that GPO-DFT has an accuracy of about 0.5 ppm, and it's sufficient to do structure determination. So, and we are within, at least for proton, we are within this range. So we can expect, as I was showing you for cocaine and SLT, we are doing pretty much the same. Yeah.
Very good.
In your motivation slide, you had an EPR spectrum, so more than one line. But then here, it's not clear to me if you show the RMSE for just one of those lines, or for all of them combined, and how do you actually make the predictions?
So the experimental is so you get this spectra, and then they extract the peaks of each of these spectra, and because actually the spread of these some sort of Gaussian are just broadening because of the experimentals.
So do you, in one single sweep, always predict more than one EPR energy?
Can you repeat?
So you use the kernel method for line everything.
Yes.
And that usually gives you one target value, but a spectrum has 10 target values or whatever. So how do you get the whole spectrum out of your method?
So so the GPO-DFT actually predicts the chemical shift, shift associated to each of the atoms within the unit cell.
Okay.
If these are proper atoms.
Okay. So
Yes. Oh, yeah, question.
yes. I saw you had one.
Oh, sure. How did you determine the weights for this NSK curve?
Brute force.
All right. Sure.
Grid search, I had a range of parameters for each part of possible. So the only intuition we had was that we were choosing from powers of 2.
Okay.
To reduce a bit the dimensionality. But yeah, it was a pure grid search and threefold cross-validation.
All right. Wow. That's a lot of individual tests.
There's one there.
Just a very quick question. The sketch apps, I assume you can use this for inorganic crystalline solids also?
Yes, because the soap similarity can work for both inorganic and organic compounds. Yes.
Last one.
So you do NMR chemical shift calculations on solids.
Yes.
So how do you treat the vector potential in the periodic boundary conditions?
So the technique is called so the GPO-DFT. So it's a question about the GPO-DFT calculation.
Yeah. So because you have the vector potential is not periodic, and you are doing a periodic calculation. Do you have some kind of a jigsaw vector potential?
That I am not
So
completely sure exactly how it is implemented in Quantum Espresso or in Castet.
But this is a fundamental problem in general. Okay, so but another thing, you didn't consider the vibrational corrections in these ones, and you had errors of about 1 ppm, and I think that vibrational contributions to an NMR chemical shift might be of the same order of magnitude.
Yes, you're right. So the molecular crystal that we are considering here for the testing were mostly rigid.
Yeah, but you had a CH vibrations, and when you're calculating or measuring the NMR chemical shift for the hydrogens or for the protons, you will get a vibrational contribution to the NMR chemical shift, and that might also be 1 ppm.
So the experts were on the NMR calculation were my collaborators. But from what I understand, you also have the broadening of the experimental chemical shift comes from these vibrational effects. So most, but it does not affect, since if I did something, let's say,
you get a shift in the resonance due to vibrations.
So perhaps we should continue this discussion afterwards, since we're already a little bit late.
Okay.
Sorry about that. Let's thank the speaker again.